Let's continue our discussion on neural networks. In this section, I want to discuss neural network examples and key considerations in neural networks. As what we discussed, right? We have an input layer, and we potentially could have multiple hidden layers in here, using one hidden layer to give you a flavor of how that would look like. And then in the hidden layer, you could use rectified linear unit ReLU as an activation function. And then on top of that, you could use a softmax activation function as a final output of your classification. So this would be one example that you have multiple inputs, and also you would have multiple outputs as well. And you can imagine that you have a different network structure that you have multiple inputs, but you only have one output. So this is something you should pay attention to. So let's use this as an example. This is coming from data camp. Let's look at, we want to predict how many transactions a person will make at a bank, which would be the dependent variable or the y variable. And then on the left-hand side in the graph, it's more simple. It says, okay, can we analyze the relationship between the number of transactions and the age or bank balance or retirement status, and all of them together, right? So we can build something like a linear regression model or a generalized linear model to describe that relationship. But on the right, things are a little bit more complicated here, where it depends on the combination of the bank balance and retirement status. You can come back with an intermediary results, which essentially is this node. And then together with this node, together with the age or some other things, you could predict the number of transactions. So essentially, you can think of this as this would be an interaction term between bank balance and retirement status, and then overall, the results might change. So theoretically, we can still do this without a neural network. But what if things become more complicated? In other words, the relationship becomes more complicated, right? That's exactly that when we could leverage neural network. So let's look at this in a different perspective, right? How we can leverage neural network in our bank transaction example. So what if, the X variables need to interact with each other? Then manually creating these interaction variables is going to be very difficult. It's no longer ideal since it's very time consuming. Plus, what if the interaction variables also wanted to interact with each other? And another hidden layer potentially could be useful as well. So this is exactly the power of neural networks. It is able to add in as many layers as possible and tease out a complex relationship. So just pay attention. Also pay attention, by the way, right? The hidden layer is made up of a set of neurons where each neuron is fully connected to all neurons in the previous layer, and where neurons in a single layer function completely independently and do not share any connections. And the last fully connected layer is called the output layer. And in classification settings, it really represents the classes that we are going to identify. So just pay attention here, right? They're independent. All these nodes in the hidden layers are independent. They're not going to impact each other. But on the other end, each one of these nodes have a relationship to all the inputs. So when you start coding, you would visually have this picture in your mind, so you would be able to understand what's out there when you started coding. Okay, so this would give you an example that in a bank transaction example, you could leverage neural networks to predict the number of transactions by introducing potentially multiple hidden layers in the model. So one thing you should be aware here, I want to define is something called forward propagation, because this is an important concept that's in neural networks. Unfortunately, actually, textbook didn't really have a lot of introduction here, so I want to give you a flavor of it. So what we do here is essentially that we want to move from the left-hand side to the right-hand side. In other words, something we call it forward, because this forward is following the direction of the arrows, right? So this methodology is called forward propagation, and the neural network model built from this is called a feed-forward neural network model, and it's one of the most basic in the field. So how do we do the calculation? So we have a weight. Before you question what is the weight, I mean how you get the weight. In this case, we actually randomly initialized. And then we have randomly initialized weight, and then based on that weight and the input. So for person who have 2 children and 3 accounts, then he potentially could have 5 in this hidden layer, hidden node, just because 2 times 1 plus 3 times 1 equals 5. Same thing for this node. It's going to be 2 times -1 plus 3 times 1, and it becomes 1. And then if, as a simple method, you would predict that this person who have 2 children and 3 accounts opening would have 9 transactions every month for the bank transactions. However, if you think about in your data, what happens is you probably have a label. You have that Y dependent variable. This type of person may not be having 9 transactions. So that's one way to think about how you can adjust the weight, so that with the hope that the number of transactions for this type of input would be close to the actual label. So that actually brings to the next step, which is something called backward propagation. But before we go there, how to adjust that weight, let's talk about the activation function first. So what we just get was, we said there's no activation function. It's simple, just forward, right? But here, once you have this activation function, what happens is instead of giving a 5 as the output of this node, or the input of the next node, then it should be 10h. If we're using 10h being the activation function, it's a 10h5 and 10h1. And with those 2 and -1 together, you can have a corresponding output as well. So that's just one step more here. This 9, most likely this would not be 9 at all. So I think this data is really, this 9 is, yeah, this may not be 9 at all, just because of this 10h function, right? So we could do some calculation to see what would be the precise number here. But the point here is, it's just simple neural network, how it's actually work, right? So activation function, and then we could also say that maybe you could leverage something like a rectified linear unit to be the function. So in that case, in this example, for example here, 3 times 4 would be 12, minus 25, it should become minus 13. And then just because we're leveraging this function, because negative 13 is less than equal to 0, it should become 0, so that this node becomes 0. So on and so forth, so that you would be able to predict the number of transactions in this example. Okay. So now let's step back. We just discussed that forward propagation. Forward propagation, we initialize the weights with a random number, and then we're trying to, with the hope that the number of transactions would match the exactly or close to the number that actual observation that you got. But it's definitely not going to happen. So you would be aware that we need to backward to adjust the weight, so that with the hope that that output is close to the actual observation. So conceptually, you would think that a small change in any weight or bias causes a small change in the output. So if we are able to figure out the relationship between the small change of the weight to the impact of the output, then because we already know how much difference of the output to the actual observation, so we would be able to come back to think, okay, let's adjust the weight correspondingly to move into the good type of directions to match the output. So that's really the general idea. And then if you look at this equation, you should be aware. So what we're really trying to do here is, this eta is something called learning rate, and then xi is the value of the i's input, and then wij is the previous weight, and the wij new weight should be based on the difference between the yj and the yj actual observation, and then the yj estimate. So if yj estimate is smaller than yj, so essentially says that the weight is from node I is not large enough yet to bring up the prediction. So that's the reason we could increase the weight by plus a eta of this difference to help us to increase the impact of the node I on the final output. That's a general concept there, so that we are able to figure out what would be the proper change of delta W. Of course, this is going to be iterative process, right? It's going to be multiple steps, so that you would be able to eventually figure out what would be the proper weight adjustment. So one of the methodology that we could leverage is something called gradient descent, which you already know. I'm assuming that not only here from this class, but also from other scenarios. So essentially what it does is we're trying to figure out what would be the direction we should be moving for that delta W, which is trying to figure out the best way to find the weights change, right? So gradient descent is used to incrementally adjust the weights to minimize error between the predicted outcome and the true outcome in a supervised deep learning framework. And then V1 and V2 would be 2 dimensions or 2 weights. It's really just for the simplified for visualization purposes. As you know, once we go beyond more than 3 dimensions, it's very difficult to visualize. And the cost function, z axis is a cost function, which is a log function. A loss function is also the objective function chosen depending on what you are modeling. Typically, it could be a quadratic loss function or MSE. It could also be cross entropy, as you may be aware, if it's going to be related to probability. So it's a little bit more math here. If a cost function is a mean squared error, as what we saw here, and then what you could do, you take the derivative of c and setting to 0 will find as a minimum. It may not be the absolute minimum, but it's a minimum, right? So you would be moving to a direction of partial order derivative in terms of V1 and partial order derivative in terms of V2 with 2 different step size of delta V1 and delta V2 would be your delta C of the cost function. And the inverse triangle C can be calculated using the derivatives of the cost function to each weight. And this can be expanded to multiple weights as well. And in terms of what you think about this graph, you can think about it's just trying to find the minimum that's going to give you the proper loss function or objective function. That's the idea of adjusting the weights to figure out where would be the best direction that you should be going to the global optimum. So that is just pay attention here, right? If you think through what we just discussed, we had a forward propagation and also leverage backward propagation to adjust weights with the hope that loss function would be minimized. And one of the approach of adjusting that weights is gradient descent. So another parameter that we just discussed is that learning rate, which is that error in the weight adjustment. Just be aware that if the learning rate is too small, which is on the left-hand side, it shows that it has slow convergence. If it's too small, keep forever to find where is a global minimum. But on the other end, if the learning rate is too big, then you could be bouncing back and forth without being able to converge to the local minimum. So as a trade-off, you could be leveraging something called vanishing gradient kind of idea. So essentially, depending on the activation function we choose, for example, is a sigmoid or 10H, as we get closer to the minimum, the gradient step gets smaller and smaller until we are inching towards the minimum, but never reach it. So a solution, this is called the vanishing gradient problem. A solution is to avoid sigma more than 10H, but use ReLU instead. So this is something you should be aware that's potentially could be some consideration in your applications. Okay, so in this section, key takeaways, we discussed, what you can do with forward propagation, what is backward propagation, and how would you be able to adjust the weights to fit the model. Okay, I'll stop here and thank you.